All right, so before the test began, because we did a bit of a review, we were working on this chapter 11, testing hypotheses, and there were some fun things that we did, right? Let's see here. Dun, dun, dun. Actually, did I forget to do another to be continued? I think I did, because we stopped right there, I believe. There, now I've put it in the right spot. But the idea was we would like to ask questions. We have some ideas of what might have happened with the data that we see, and we want to know, like, is this really what happened? Did something weird take place? And so we learned how to simulate a bunch of different ideas. Kind of the coolest one, in my opinion, that we talked about, this kind of was very enlightening, was our Gregor Mendel example, where he found that when he grew a bunch of pea plants, 929 total, he worked very hard planting them all, he found that about 75% of them were purple flowers rather than white flowers. And he's like, nature probably works in 3/4 ratios rather than 7, 5, 8, 9 over 10,000 ratios. And so that makes sense. And that was his model, right? That was his idea of how the world worked. It's like, all right, there must be maybe deep down a secretly 75% chance that there will be purple flowers, a 25% chance that there will be white flowers, and everything else that we saw, this wasn't exactly 75%, but if you flip a coin a couple times, you might get more heads than expected, right? If you flip a coin twice, you might get 2 heads, which is not always the case, right? So maybe this was due just to random chance, and that becomes your null hypothesis. That's what that is called. Did we have that here somewhere? There it is. Your null hypothesis is something you can simulate. It's your idea of the world. Like, okay, everything that I saw in this data set, all the differences that I see are just due to completely random chance. There was no difference other than random chance. And we can simulate that with our computers, of course. And if during the course of our simulation, like we planted a bunch of virtual pea plant gardens, and we saw, like, all right, how often, if there really was a perfect 75-25 split, and that was what we were drawing from in our simulation, how often do we see a garden that has a little bit more than 75% purple flowers? And so we can do that kind of simulation. If our simulation shows that it is possible, it was quite likely to see something just a little bit above 75%, not exactly, but a little bit above, then that means that our null hypothesis model kind of predicts our data pretty well, and maybe that means that it really was just due to random chance, and so we can conclude that. If we notice that our data that we're getting from our null hypothesis, from our simulation, is not quite the same, it's not very well predicted, it's very unlikely that we see the value that we saw in real life from the model generated from our null hypothesis, then that leads us to reject, we say, the null hypothesis in favor of some alternative hypothesis. That's like, all right, maybe there was something other than just randomness at play here. We better go figure out what. Okay? And so the number that kind of tells us what the difference is was our p-value. Our p-value is the chance that, like, our null hypothesis can predict the data that we saw. And we calculated that for a few different ideas, right? Dun, dun, dun. Where was here was our Mendel example. So we did a bunch of those, and we saw that, what we saw in real life was pretty well predicted by our model. How often did we see a value like this, or even more extreme? Over half of the time. So that means it really probably was just due to random chance. I think we know from genetics now that it really was like a 3/4 chance perfectly, but they didn't at the time. And so now we can, even with statistics, conclude it. It's beautiful. All right. So yeah, we did some more examples. We did a midterm scores example after that. That's kind of where we left off. All right. We want to formulate. We've got some data. We would like to test whether the differences that we see in the data are due to random chance after we've come up with some model, some simulatable way of predicting what might have happened. And we want to see how often does our simulation predict what we saw, and we can come up with a number based on that. All right, so that's kind of a recap of where we were. Are there any questions about that before I show us a new data set and we do the same thing all over again? So that's where I want to be. All right. So here's a fun little data set I found as I was working on these slides back when I was making them for the first time. I found a data set for people eating fish. All right, people in Sweden eating fish. So of course I have the little Swedish fish up here. So it was from 2001. The study was done, and they tracked over 6,000 Swedish men for 30 years to see, does eating fish affect whether or not you get prostate cancer as a man? So it's interesting, right? They also, the original studies was pretty cool. They used twins. They used pairs of twins, only twins, so that there really was no difference other than like, did this twin ate more fish than this other twin, which is crazy and very interesting. So there's a lot of twins in Sweden apparently, and they all signed up for this study, which was great. So yeah, that let them really tell the difference because there's no genetic difference, right, between twins. That's pretty cool. So they discovered with their statistical tests, whatever they used, it wasn't Python probably, but they were able to tell that the risk of cancer for those who never ate fish was substantially greater. So maybe that means we should all eat fish as men. So yeah, we can test this. We've got the data. All right, we've got the data, and I'll load it up and we'll do some tests in a second. But kind of the null hypothesis in this case is something that's simulatable, something that we can figure out based on the data. What we're going to have is just a bunch of people here. Let's load in the data first before we talk about the null hypothesis. Fish diet. So it's table, read table. It's legitimately called fish-diet.csv in my data folder. So here is, oh, sorry. I'm going to need to include our library. That would be necessary. Boop. There we go. So you just got a bunch of rows that look like this. You've got how often did these people eat fish throughout the study. It's probably easier to just go to the thing. It'll be a little small, sorry. You got like never. They never ate fish. They ate a small amount of fish. They ate a moderate amount of fish. They ate a large amount of fish. So that's one column. And then the other column is just yes or no. It's cancer. Did throughout the study, as they were taking the study, did this man from in this particular row that they tracked, did he end up getting or contracting prostate cancer? Okay, so that's what happened. That's how they made their data, and that's what it looks like. So yeah, if we do another thing I could have done is done like a sample of 10 or something to show like here's the kinds of values that we get. Moderate amounts of small amounts of fish diet, fish, moderate amounts of fish, large amounts of fish, and then no or yes, did this person get cancer or did not get cancer? Okay, so those are all the values that we have. That's the data that we have on each person. Not too much. But now, if we want to form an experiment to say, like, to test, right, did eating more fish cause less cancer? It's kind of what we're trying to find out. Like, was there really a cause there? Our null hypothesis should always be, like, not believing in anything other than random chance, right? Because that's something that we can simulate. So when we're trying to formulate a null hypothesis, that's what needs to be in the back of our minds. It's like, all right, what can I simulate? What is just like everything is perfectly random? What does that mean for this study? What can we simulate about that? It's going to be something like this. It's going to be like, all right, the cancer rate for men was completely constant. It did not depend on fish consumption. It's just like completely random whether this person, they got prostate cancer or not. Had nothing to do with their fish intake. Does that kind of make sense? Like there was no difference in the population other than complete randomness telling them who got cancer and who didn't get cancer. Okay? So that's kind of how that works. Okay? And so, yeah, like there is, we're going to come back to this study in the next chapter because there's kind of a better way to do this. But when we're trying to do this, we do have to pick a number right now. Well, I'll show you later that we don't have to eventually, but at least with our current knowledge, it's like, all right, the cancer rate for men is a constant rate that doesn't depend on fish consumption. Like, what is it? Is it 50%? Is it 25%? Like, Mendel had a number, right? He was like, all right, it's 75. This is my model. We kind of need a number here, and we don't have one. So kind of the best thing that we can do with our current knowledge. There's a way to get around this in the next chapter. We'll get there. But with our current knowledge, we can just use the sample's cancer rate. Just like, all right, here are all the people who got cancer and did not get cancer. Let's just kind of count them up. All right. So diet dot, not sample. Let's do a group on these people. Group on the diet column. And so this is how many people ate small amounts of fish, never ate fish, moderate amounts of fish, large amounts of fish in their diet. And we can also, remember, in a group, you can group multiple things if you give it as an array or just some sequence. So I can group on the following, and it will group on every possibility of these columns. Group on both diet and cancer. And then it'll count things for me. All right? So that's what it's doing. It's grouping both on diet and cancer. So for every combination of diet and cancer, it is giving me counts. So all right, for people who ate large amounts of fish, this many people did not get prostate cancer. This many men did get prostate cancer. For moderate amount fish eaters, this many people in the study did not get cancer. This many people did, and so on and so forth. All right. So those kinds of numbers are kind of useful for us. Another way to kind of do this, because there's two variables involved now, is we could have done a pivot. All right. So we're just kind of exploring the data right now. But if you do a pivot, you got to give both things. What do you want on the x-axis? What do you want on the y? So I think I want, if you do it like this, diet is on the x and cancer is on the y. You could have also done it the other way with cancer on the x and diet on the y. There we go. So for people who never ate fish, this many people did, 110 of them did not get cancer, and 14 of them did get prostate cancer. And so now, kind of what we want to do is let's get the rates. Let's get the cancer rates for all these people, because surely they found something in the study. We should be looking at that, right? So let's get these cancer rates. So let's see. Let's take this pivot table, because I kind of want to divide, right? Kind of want to divide the yeses by like the total amounts, because that will give me cancer rate for each of these different groups. So let's make this pivot table. Let's call it something. I'll call it like diet 2. Diet. Call it diet pivot. But like now I have this as a table. I've called this table diet 2 now, and I can say, all right, give me that column for yes, and I want to divide it by just like all the people total, which is the yeses plus the no's, right? I got to put that in parentheses. So if I do this formula right here, do you see how that's going to give me the cancer rate for each of those different populations, for each of those different diets? It's going to divide all the yeses by the sums of the yeses and the no's. So like it'll do the 42 over 42 plus 5 over 7. It's going to give me the rate for the large fish eaters, large amounts of fish eaters. And it looks like for them it was about 7.7% chance of them getting cancer. For the moderate fish eaters, about 7% of them getting a chance of having cancer. For the never fish eaters, you see that there's a 11.3% chance of them getting prostate cancer. And then for the small amount of fish eaters is like 7.7 again. So I guess that means we should all be eating a moderate amount of fish as guys. Who knows? But notice that it's within the 7s for everybody but the nevers. Right? For everybody but the nevers. What's the total rate of cancer among all of these people? Because our null hypothesis is like, all right, the cancer rate was just completely random. Those people who never ate fish for this particular study, they just got lucky or unlucky, depending on how you think about it. There was no reason, right? It was just completely due to chance. Fish had nothing to do with the equation. The cancer rate for men is just completely constant, has nothing to do with fish consumption, all right? So we need a number. Do we choose like 7.6? Or we don't know what percentage to choose right now. Let's take let's just take the entire amounts of like cancer rate. So to get the total cancer rate for everybody, to get everybody's cancer rate, you can take all the yeses, sum of all the yeses, divided by like everybody in the study. Does that kind of make sense? So I take diet 2, I take all the yeses, right? That's the 42, 209, 14, 201. And I sum those up, give them to the sum function. This is all the people in the study who got prostate cancer, regardless of their fish consumption. And if I take that and I divide it by just like everybody in the study, which is like the yeses plus the nos, or just like every row in the original table, diet.num rows, all the 6,000-ish people, that'll work too. So this will give me the total cancer rate among everybody in the study. And that's like 7.4-ish%. Okay? So that's the total cancer rate, and that's probably the best thing that we have right now to use for our null hypothesis. Just like, all right, that must have been the true rate of getting cancer, and then everybody in the never group just got really unlucky. It was a small group because they must eat a lot of fish in Sweden, but the differences that we saw, we're just assuming it was due to random chance, and the true rate of getting cancer, let's just assume it was the statistic from our sample of just like the cancer rate for everybody, okay? That is going to be, that's going to be our proportion for our model. So just like we were doing for Mendel, we were assuming that the proportion was exactly a 75-25 split. We're going to do the same thing. We're going to assume that the cancer proportion, right, it's going to be our model proportions, is going to be something similar to that, all right? And so this was the proportion from the sample of people getting cancer. So I'll call this sample proportion. Yeah, and so what I want to do now is call sample proportions, where we kind of make a random group of people, right? We want to come up with a random group of people, and our proportions for like whether or not they get cancer is this array, right? With our sample proportions are 7.5-ish%, and then everything, like that's the proportion of them getting cancer. Let's assume that that's a real percentage chance that someone just gets prostate cancer in the wild. And then 1 minus that is going to be the chance that they don't have prostate cancer, right? So that's going to be our split. We're going to pretend that that's the real true cancer rate for everybody, and that's simulatable now. All right, with our null hypothesis, we're just going to assume that, all right, there was a constant rate of people getting cancer. The people in the never group just happened to get unlucky and get more cancer than usual. So that group of, 124 men, we can simulate again with these proportions. Does that make sense what we're about to do? That can be our null hypothesis simulation. All right, so we want to do that. We want to do sample proportions of 110 plus 14, 124, right? We could type it out, or we can have it do it. And then we want to know, all right, make a group of that many men, assuming that this was the underlying chance of them getting cancer. How often do I see 11.3% of them getting cancer under the assumption that it really was just this much smaller amount rate that people got prostate cancer with? And so if I keep running this, hopefully you can kind of see, it's making groups of 124 men secretly, drawing from this proportion of cancer rates, and it's telling me how many of those simulated 124 men got cancer and did not get cancer. Does that idea make sense? And you see here, sometimes it is quite large and it's close to the value that we saw here, which is awesome. Or not awesome, it's just like it shows that it's possible for our model to sometimes predict it, right? It was almost spot on. So, but usually it's going to be close to that original value. So if under this assumption, right, this is our null hypothesis, we're assuming that the rate was just completely the same for everybody, and all the differences that we saw in the groups had nothing to do with fish consumption, it just had to do with complete and utter randomness. So as we do this simulation, we just kind of want to keep track of like how often did this simulated group of men get cancer. So I want the first thing in this array that I'm given back to me. So I want .item0 for my simulation. So a very small group of men getting, simulated people getting cancer in this case. And so that's a cancer rate for a simulated group of the same amount of men who had a really high chance in our original study. All right. We want to see how often this happened due to chance with this much smaller rate of cancer. Because you know that if you flip a couple coins, sometimes they might all land on heads. It'll eventually happen. So maybe this is what happened in the study. We want to see how often that takes place. And that'll cause us to either accept that our null hypothesis is probably true or reject it in favor of the idea that, okay, maybe fish consumption really did matter. All right. So I want to simulate a rate of cancer. I'll call this one simulated rate. That's kind of how your book likes to label these and name them. And I really just want to return this idea. It's a very long line now, sorry. But it's just do all this all over again. Take a sample, simulate a group of just as many men as were in the study that had the weird higher than usual percentage, and then assume that everybody had the same chance of getting cancer, which was the sample's proportion, and see how many in this simulation got cancer. Unsimulated rate, if I call it, only 4.8% of the simulated men in this one got cancer, and if I rerun it, of course, I get another sample. It's very even smaller this time. Crazy. So that's possible. And so what I want to do now is I want to do this a few thousand times, just like we were doing before. I want to stop like 10,000 times. That's a good number that your book likes to use. 10,000 simulations, and you could change this variable, of course. I want to simulate a bunch of rates, a bunch of cancer rates, assuming that the cancer rate's the same for everybody. The one that we found for just the total, for all the men combined. I'll call this simulated rates is a new array that is empty. And like for every simulation, what I want to do is tack on, like have one new simulated rate, np.append that to my array that's keeping track of everyone that I've seen, and just like add it in. Just keep on adding it in. And so 10,000 times, blink of an eye for the computer, at least for this simulation. And now I've got a bunch of simulated cancer rates. Sometimes they're smaller than the group that we saw in real life. Sometimes they're right on track, right, with the group that we found in real life. And we want to see if this was really due to randomness, this large proportion. We should see this like 11%, 11.3-ish cancer rate percentage show up a little bit sometimes, all right? We should see it decently often if it was just due to randomness, all right? So let's see. So what we want to do is we want to make a table so we can see a histogram of it. That would be the first idea with column, call it rates, simulated rates. And then I want to make, so I'll just give me a table with all these things in it, because then I can do a dot histogram, right? On column number 0, or just like rates column. And maybe let's do a few more bins. Let's do like 20 bins in the default way that it likes to do it. And nice. So here's what we got. And the value that we saw in real life was like 11.3-ish, so somewhere over here. And it looks like it is sometimes predicted by our model. Sometimes, if there was just a 7-ish% chance deep down of people getting cancer, for a group of 124 people, just due to complete randomness, you would sometimes see a value as extreme or more extreme as we saw in the study. And so we can come up with a p-value now, like what is the percentage chance that if we did this all over again, like we'd see a value that extreme or more extreme. What's the percentage chance that our model kind of predicts this value that we saw in real life, right? And that's going to be, you take your rates, you see how they compare, like how often were they equal to the weird value that we thought was a little too large, this 0.1129, right? How often was it that or something even more extreme, which was farther away, right, from the smaller number, so bigger than or equal to. How often was it bigger than or equal to that? And we can do an np.count non-zero, right? 388 times. Out of how many times? It was, you can divide by simulations, which is 10,000, or you can be like, divide by the length of simulated rates, just in case you changed it. That'll also give you 10,000, right? And so it looks like 3.88% of the time, our model gives us a value that extreme or worse, or even more extreme. And so that kind of goes to show that, all right, if it really was due to random chance, we were in one of these 4-ish% of the universe is where that might have happened. So that kind of makes sense. There's like a 4% chance-ish that we would see a value this far off if the true cancer rate did not depend on fish consumption. Yeah? That's kind of the number that we'd see. Okay? So everybody in the statistics world is like anything a p-value that's less than 5% or equal to it is statistically significant. It's like less than a 1 in 20% chance, right? For less than a 1 in 25% chance for us. Now, 1 in 25 chance that our model would predict this happening, and that's pretty unlikely. So that usually causes us to reject. We reject our null hypothesis, and we reject our null hypothesis, and we believe that there was something else that was due to random chance, right? Other than random chance that was causing this problem. All right? Does that kind of make sense, that conclusion? That's kind of interesting, right? That's kind of fun. So let's see. What else do I want to do? Dun, dun, dun. Yeah. This may feel a little wrong to you right now because we kind of had to come up with a number, and that number was just like something that we guessed based on our sample, which is, I guess, kind of similar to what Mendel did, but it wasn't like a perfect 3/4 chance. This was just like a weird number that we saw. We kind of had to guess, just like Mendel, right? Just like Mendel, we had to guess a cancer rate for the entire population to make our model, right? Let's type this for posterity. And that sometimes feels wrong. It's like we're making up numbers almost, right? And that feels a little wrong. It doesn't, it's not horrible because that's exactly what Mendel did, so it shouldn't make you feel too bad, but like that might make you feel a little uneasy right now, and I accept that. All right? We will see a better way to do this. I feel as uneasy as you do, so we'll see a better way to do this same experiment kind of test in the next chapter. And it's going to be a little bit similar to what we did for the midterm, almost. Because I can kind of explain where we're going with that midterm example. Remember what we did for that one? We had a group of people. I guess this was pretend, but like there was a bunch of different lab sections of students, like maybe in a physics class that took a midterm. The midterm was out of 25 points, and we saw that there was a certain section number 3, that had a very low average, and we're like, was that just due to random chance or wasn't it? And so what we did was we simulated a bunch of random section 3s by taking people from every section. We simulated a bunch of random section 3s of the same original size by taking a sample of the entire population and like pretending, okay, you're all in section 3 now. Okay, that's what we did. And we could also do that. We could play that game here as well. We could make a bunch of random from our original data set. That's kind of what the next chapter is going to show us in a different kind of way. We can make a bunch of like, we can just take a bunch of random people from this and pretend that these are the never eaters, right? It's like just take a sample and pretend that these people were the group that we were worried about. All right, so that's treating it like the midterm scores. All right, let me show you what I mean by that. Let's try to treat, because that's another way we could do the same simulation. Treat or ask the same question. Treat this data set like the midterm scores example. Because what we did there, remember, was we just kind of picked our random group of people to be that section 3. We could again do the same thing. We could pick a random group of people. Like if there was no difference between like the people who ate fish and the people who didn't eat too much fish, then it doesn't matter who I pretend is in the never group. Does that kind of make sense? That's the idea. So yeah. Yeah, let's do it like this. So we did have a bunch of numbers, though, by the way. back here. We had scores, sections and scores and things. So let's do, let's turn some of these ideas into numbers. All right, so let's turn cancer into a number, yes or no. Okay, let's turn it into a 1 if it was yes and a no if it was 0. I'm going somewhere with this. All right, so let's make that happen. So I'll say def. I'm going to make a function that I apply to the diet table that turns the yeses into 1s and the nos into 0s. Right? Cancer to number. That's going to be my function is going to take that string yes or no, right? And so if yes or no, that value that I'm getting right now happened to be yes, then I'll give back 1. Otherwise, I'll give back 0. And so this is going to turn all the yeses or nos into 1s or 0s. All right, and that will let me do some fun math in just a second. Okay, it'll make it easy to do a recalculation. So I'll call this. Yeah. So first of all, this function works like this: you give it yes, or you give it no, it gives you 0, right? It gives back 0 for no, and 1 for yes. And so I can apply that to this table, where I can say take the diet table and apply that cancer to number function to the cancer column. And now I get a bunch of 1s and 0s for how often there was yeses or nos. And I can add that back into the table. I'll call it like diet 3 equals take the original diet table, add a new column with that idea. All right, cancer as a number. And I'll call that diet 3. And so now, just like every time it said yes, I've got a 1 over here. Every time it said no, I've got a 0 over there. All right. Because the goal now, and the reason I did 1s and 0s is because we can do a rate calculation very easily. The goal now is, just like for the midterm group, we don't have to come up with a random idea of like, okay, this was the true rate of getting cancer. We don't have to think about that anymore. We can just pick a random group of people, pretend that that's the never group now. Because if nothing mattered, if your fish consumption didn't matter, then I can just pick anybody. I can pick at random amounts of random 124 people, see if they had cancer or not. Like, that's my new never group, because it shouldn't have mattered if you had cancer. So that's kind of what we want to do. You want to do like diet 3, sample 124 people. Do not duplicate anybody, though. We're like trying to take people from the study, not trying to clone them at all. So with replacement equals false. And this is a random group now that can be our never group. Does that kind of make sense what I'm doing there? I'm just picking from the entire population, because if fish consumption didn't matter, then this diet column was useless. You just give me 124 random people, then we'll see how often they got cancer or not. That's my new null hypothesis simulation. So random group. Boop. So you can call that whatever you want. And the way that you can take this group, because it's like 124 rows, the reason I made this a number, 0s or 1s, is you can get the cancer rate for this random group by just taking the average of that column now. Does that kind of make sense? You can go to your random group, you can say, go to that column called cancer's number, and then you got a bunch of 1s and 0s, and what you want to do is like, what was the cancer rate of this random group? Well, it's just like add up all the 1s, divide by the total, which is the same as doing the average, mean. Does that kind of make sense? Because it's adding them all up, dividing by the total. And if there's 1s in the places you cared about, it's like, here is the format random group. Here was the chance of them getting cancer. And so now I don't have to make up a number. Now I can just like draw people as a sample from my population, because it shouldn't have mattered, right? If the diet column didn't matter, then maybe we just got a really unlucky group for these never people. And if I draw again 124 people, then we'll see how often. If it was truly random, we'll see if I just draw 124 random people a bunch of times, we'll see how often I got a number this large. Because then, I don't have to come up with an initial value and do sample proportions. I can just like make a random group. Okay? That idea, that difference in that idea makes sense. Like I don't have to come up with a magic number anymore. Not to say that that was a bad thing. That's what Mendel did. This is another way of doing the test. This is more similar to the midterm test example. midterm scores thing. So I just want to do this a bunch of times. I want to make a bunch of random groups and get a bunch of cancer rates, and that's another way to simulate this idea. Like, how often did I see a group, if this didn't matter, how often did I see a group that large of the same size with a cancer rate as big as we saw for that never group? So yeah, make another random group. Get the cancer rate for that random group. Return that. And then do that a bunch of times. So I'll just do it quickly. I'll do my little simulations again. I use the same function name. And it should just be able to copy and paste this, right? One simulated rate. I do that a bunch of times, and now, boop, it's a bit harder to do sampling, so that takes a bit longer, but fast enough. And if I do this again, boop, here's another histogram in kind of a similar style, but I hope you see what's going on. It is what we've done this time, right? To check, we're again assuming that there was no difference for anybody, and oops, there was no difference for the cancer rate of men, depending on whether or not they ate fish. It did not matter, and so I made a bunch of random groups of the same size as the size of that group we were worried about, and we got a bunch of cancer rates for those random groups. We were simulating. Didn't matter if they ate fish or not. How often do we see a value as large as we saw in real life? Like something over here bigger. It looks like our model is predicting this value, that it is possible. How often do we see a value that was as big as or bigger than? More extreme, right? And the number we saw for that never ate fish group. This one's slightly bigger. It's a little over 4% this time. It's like 3.88 before. So like 4.2%. 4.26% chance under this method of simulation that our null hypothesis model predicts what we saw. Again, it's less than 5 though, so that leads us to reject our null hypothesis and say, it's pretty unlikely that that never group was just due to random chance. It's due to random chance, and there was the same rate for everybody of getting cancer. It's very, very unlikely. It's less than 1 in 20, right? And so that leads us to imagine that the universe probably doesn't work that way. We didn't get that unlucky, most likely. So let's conclude that there must have been something else at play. And therefore, there must be something with fish, all right? It seems like if you eat a little bit of fish, it's less likely for you to get cancer. And that's good to know. Awesome. And I think that's what I wanted to say about this example. So are there any questions about how we came up with null hypotheses? Because we did it twice. We did it in 2 different ways. But do you see how we're simulating things? The backbone of the idea is always that something is due to complete random chance. There's nothing else. That's our null hypothesis. That's our simulatable model. And then we see how often did our model predict the extreme value or some that we saw in real life that we were worried about. That's the reason we asked the question in the first place. How often did we see a value that extreme or even more extreme, whichever direction that matters to you? And then we get a p-value. We see how often our model predicts that value that we saw. And if it's really small, that leads us to reject our null hypothesis and be like, no, probably there's something else going on. Okay? Yeah, any questions about that example? Because then I want you to try. All right. So let me give you all the code that I have written so far. Because I'm going to ask you to do similar things. If you want to look at the stuff that we did today, that works too. But also the stuff from last time is good knowledge. But I've given you all the code for our chapter 11 file if you want to look at it. But my question to you now is, let's go to the Titanic data set. All right. My question to you is, were women actually more likely to survive the Titanic? Were they more likely to survive the Titanic? The first question that you need to think about is, what in the world is the null hypothesis here? How am I going to simulate whether or not women were more likely to survive the Titanic? So you're going to read in the data set, and you're going to get some data. You're going to try to figure this out, right? So think about what your null hypothesis needs to be. Remember that the null hypothesis here that we used for fish diet, for the first time at least, was something like this. This is our simulatable idea. can you kind of do something similar for Titanic? I'll give you a minute to think about the null hypothesis. We'll write one down that we can agree on. Or I'll write it down for us. So I want us to use it, but think about the null hypothesis for a minute as I talk, and then we do want you to try to do a simulation too. We decided on the null hypothesis. What's something? How would you explain it? It's completely due to chance. Any difference that we saw is completely due to chance regarding this question. I think about that. All right, let's think about the null hypothesis, and then I'll give you some time to try to do the simulation too. But let's read in the table. Because the question is, like, were women more likely to survive the Titanic? We need to see, like, okay, were they? What does that even mean for us? So we know the sex of the passengers, and we know if they survived or did not survive. And so we kind of need a proportion now. We want to know how many women, what's the proportion of women who survived versus proportion of men who survived, right? So we need that. Get the proportion of women who survived. And then Titanic dot where survived values are equal to 1, right? Because that's the survivors. So here's every survivor. And then I want to group it by the sex, right? Group by sex. And so, like, were women more likely to survive the Titanic? Well, it looks like, yeah, at least as far as this goes. What's the number here? It's just like, all right, what's the proportion of women to men? 233 over 233 plus 109. It looks like there was a 68% of the people who survived were women. Yeah? Does that kind of make sense how we figured that out? 68% of the people who survived were women. That's one way to think about it, right? Like the people who survived total. Or you could also think about it. I think the question you could also pose it in another way. Just like, all right, look at only the women on the Titanic. How many of them survived versus did not survive? So that's the other way of thinking about this. There's two options, right? Titanic.where the sex is female. So here's every woman on the Titanic, and then we can group by whether or not they survived. So it looks like, again, 233 of them survived out of how many women total? 233 plus 81. And that's a bit of a higher percentage. You see that those are two different ways to answer the question, and you have to kind of decide, like, what was the actual proportion I'm looking against right now? Honestly, when I look at this question, it makes me think about women only, not women versus men. So I would like to think that probably the correct proportion of survivors for women is maybe the second one. The second one right here is almost 75%. But you could disagree with me. You could make it that one. Doesn't matter. I think this second one is the correct proportion of survivors. So that's what we saw in real life. If there was no, like the null hypothesis, right, is kind of the idea if there was no difference. Is that what we decided? There was no difference in the survival rate for women. It wasn't, they weren't more likely or less likely to survive. Any difference that we see is random chance. So that's kind of going to be our null hypothesis. You kind of see that? Null hypothesis, that's something we can simulate. Boop. So everybody was equally likely to survive, or men and women were equally likely to survive. And the difference that we see was due to random chance. And so how will you simulate this? You probably use a 50-50 proportion. Does that kind of make sense? Like, all right, the chance of somebody surviving versus not surviving, like the chance of you picking up a guy or a girl is like 50-50. It doesn't matter. The gender did not matter. So that's what we're trying to simulate. And honestly, you could use either of these. You have two options. This is another way of asking the question, right? This is men versus women. This is women only survivors. What do you want to simulate against? Is kind of the question. Okay, that's our first step, and these are the proportions that we saw in real life. So you got to decide, like, all right, is it women versus men, or just women total? Are women more likely to survive the Titanic? And so you can ask the question, like, all right, there's probably maybe there's like a 50-50 chance of them surviving or getting chosen versus their male counterparts. And so, yeah, there's a couple different ways to think about it. Just for fun, maybe we can do this first one, men versus women. So that's going to lead us to step 2, right? I'll try to break this down. You guys can try, go ahead of me if you want to. But that's going to be like step 2. We should probably simulate, right? Simulate a group. Let's go with the first way. Let's go with the first option for fun. All right. So let's say it was all right. It's women versus men, survivors, 68% chance. There's quite a bit more women than men. So let's simulate a group of men and women. Let's see, a group of 233 plus 109 people, right? People under the null hypothesis model, where men and women are equally likely to survive. And get the proportion of women survivors. Does that kind of make sense, what you do next? It's like, all right, this is what we saw in real life. It was a bit bigger than 50-50 split for men versus women. So we could simulate, if we're going to assume that there was no difference, right? Assuming the null hypothesis was true, women weren't any more likely than men. It was a 50-50 split. That's their only option at this point, right? If there's no difference, then simulate a group of that exact many people, same amount of survivors as were on the real Titanic, simulate exactly that many people under that model of a 50-50 split, and figure out what proportion of women survived. So that's going to be a call to sample proportions, right? So think about that. Give you a minute, and then we'll just do it together, but slowly. Okay, and let me know if you have any questions. Try to call sample proportions if you haven't already, with a 50-50 split. I think we've done that already for like coins, right? Heads and tails. We called sample proportions in that way before. Makes sense. So, all right, let's do that. This is how I would call it. I call it sample proportions. And you give it, all right, how many people are you trying to simulate? 233 plus 109, whatever that is. Let Python do the math. And then you give it an array of proportions. How likely was one group to survive? How likely was the other group to survive? Let's say it's a 50-50 split. Doesn't matter which one was women for, like, was it men then women or women then men? Doesn't matter as long as you're consistent. So like if there's a 50-50 split, let's say that it was men then women. Just like, all right, for this sample set of Titanic survivors, assuming that there was no difference in whether or not a woman or a man was saved, then there is a little bit less men, a little bit more women for this simulation. Does that kind of make sense? A little bit more men, a little bit less women this time. It's always like that. Okay? So now you kind of want to do this a bunch of times, right? So that's our next step. So step 3, make a function to create a random sample and get the survivor rate from it. And then you want to run your function a few thousand times, do like 10,000 times. Run your function 10,000 times, saving the rate you get each time. So you do have to go into this, like go to .item 1 if you're going to assume that the second thing is the women percentage. Go to .item 0 if you think it's the first one is the women percentage, whatever you want. But do that a bunch of times, and the question is now, how often do you see a value this extreme? If it really was a 50-50 split, there was no difference in them wanting to save a woman versus a man, how often did we see a value as extreme or even more extreme as this one? Does that make sense? That's what you're trying to simulate now. So I'll give you another minute to try that, and then I'll do it too. But do let me know if you have any questions, because this is how we learn. We try it out. Here. All right, you can keep working if you're still going, but I'm going to give you my thoughts now. So again, we're making like a survivor rate. So I'll make a function called give me one simulated rate. That's what we like to call those things. And so I want to do this. I want to do this and get the women survivor rates, and that implies I need to go to like .item 1 or something if 1 is going to be the women rate. Or 0, just as long as you're consistent. So there's my, assuming it was a perfect 50-50 split of who they chose to survive. Let's pick there, and let's do a bunch of simulations. Let's get them all together. I think I said the same function name. I've overwritten it, so that's perfect. So a bunch of simulator rates again. Let's do it all over again. And so I've got a bunch of percentages. Some of them are a little bit for women survivors amounts. Some of them are less than 50. Some of them are over 50. And the question is, how many of them were 68? Yeah, because that's what we're assuming. We're assuming there was no difference. That's our null hypothesis. So we want to know, like, how good of a job was that? doing, right? So that's our last step. We want to calculate a p-value. We want to create a histogram. So I want you to try that. So please create a histogram of these rates that we've made and see how likely, also by getting a p-value, how likely did we see a value that was as extreme or more extreme than what we saw in real life? How likely it is to get a rate as high as we saw, or even higher. All right, and that implies, so calculate a p-value. All right, so I've done that for other things. You try it too. It's going to be the same code because we used the same names for the array. Simulated rates is what it's still called. But I hope you see how this answers our question. Like, all right, if it really was, there was no difference in men versus women, this is what should have happened, and then there's all of these different simulated universes. How often do we simulate something we saw in real life, or even more extreme? All right, and so it's just going to be this code all over again. So I use the same name. Do I want 20 bends again? Sure I do. Why not? So look at how all of what we see are kind of centered around 50%, because like that's what we assumed. That's what our model was assuming happened. And we saw like 68% women survived versus men in real life. And that's off the chart. That's something that our model isn't even predicting. It's possible, right? That would be like rolling a bunch of coins and they all landed heads almost. Like rolling 1,000 coins and 750 of them landing on heads. It happens eventually, but it'll take a million billion different simulations. So it's very unlikely. And so if we want to take a number to that, we're going to make our p-value by taking, all right, how often did we get a rate that was equal to or even more extreme than, so bigger than, what we saw in real life, which was this 68.12%. Bigger than or equal to that? Never. Looks like there is 0 times did our model predict that in all the 10,000 simulations. And so do you see how what you do then is you'd be like, all right, our null hypothesis does not predict this value that we saw. Our null hypothesis, where we're assuming that women and men were equally likely to survive, it was a 50-50 split of who they would take. They just randomly took a bunch more women. We reject that now, we say. We reject, our conclusion is we reject the null hypothesis. Conclusion. We reject the null hypothesis. It wasn't just due to random chance. We're not simulating anything like that. So it must be that there's something about they were trying to save women more than men. So that's kind of interesting, right? Does that make sense how we asked that question, then we answered it as well? The concrete number using our simulations. It looks like this is making me log in, so let me fix that real quick. I have no idea why it's doing this right now, but we'll figure it out. Hi. Huh? It's never done that, as long as I can remember. They must have logged me out for some reason. Yeah, sure. That's so weird. I hope it's happy now. I guess it is. But yeah, we rejected our null hypothesis in favor of an alternative. It was probably that they were thinking to save women. Does that make sense how we asked the question and answered it? We'll have to deal with that later, I guess. But yeah, that was one. And then I have one last one for us to try. I want to talk about cereal. All right, so let's go get the cereal data set and remember what was going on there. This is a fun one. So our cereal data set is just like table, read table. I called it cereal.csv. This is from a study in the late 80s, early 90s. And we remembered that the shelves, right, were ordered from bottom to top. So if shelf 1 was closest to the ground, shelf 2 was middle shelf, shelf 3 was the highest shelf. And we saw that shelf 2's cereals were abnormally sugary, which is kind of goes along with the idea that they were trying to put those at the eye level of toddlers so they could ask their parents to get that for them. Because we know that kids like sugar. So let's go to this table and let's remember the differences so that we can be surprised again. Let's select out the shelf column and the sugars column. So that's all we really need. And then let's group by shelf. These are the numbers of cereals on each shelf. Doesn't really matter. But let's instead of getting how many were on each shelf, let's aggregate by taking the average amounts of those sugars. So np.average on everything else, which is just the sugars column. And you see that there is, on average, 9.62-ish grams of sugar on shelf 2, and that's way more than the other shelves. Yeah, way more than the other shelves. So how many things, how many pieces of cereal, or how many boxes or different brands of cereal, different items were on shelf 2? There were 21 of them. And so kind of what we should be doing is coming up with a null hypothesis and trying to do a simulation to see, like, was it true? Were cereals on shelf 2 really selected to be extra sugary, or did they just, like, all right, they were taking them off the truck and they just happened to put the sugary ones right there? Was it due to randomness or was it not? That's our question right now. So let's assume that, let's use this null hypothesis. Let's say that shelf 2's high sugar average was completely due to randomness. And so what that means is they just got lucky, right? That means that they picked how many? 21 random cereals, and they just happen to be extra sugary. That's what we're assuming right now. Does that make sense? How that's the null hypothesis? That's something that we can simulate? Because that's what you can do now. To test this under the null hypothesis, what you can do is you can go and take from the data set, make a random shelf 2. Does that make sense? Go and get 21 cereals from the data set. This is like the second way that we made the fish hypothesis test. This is the way that we did the midterm scores hypothesis test. Go and simulate a shelf 2 with exactly as many cereals as was actually on it, 21. Go and get 21 cereals from the data set and pretend that those random 21, that sample, it's going to be a sample, right? Pretend that those 21 were your shelf 2. Does that make sense? That's how you can simulate this. Because then you can check, all right, on that simulated shelf 2, what was the average amount of sugar? And then you can compare. You see where you can go with that? So give that a try. I'll give you a couple minutes to try that. But that's going to be the setup. So you're going to want to make a function. Maybe just try it out with outside of the curve. You'll want to make a function, it's like one simulated average or something. You want to make a random shelf 2 with as many cereals as are actually on it, right? As many cereals as are actually on it. Each time you get that random cereal sample, and pretend shelf 2, you see how much sugar was in that random shelf 2, because we're assuming it was due to randomness that we saw a value so large. So get those values and save them a few thousand times, right? Like 10,000 times, get a bunch of shelf 2 average random sugar amounts. And then you'll make a histogram, you'll compare that, right? To get your p-value, you'll compare those values to the extreme value that we saw, over 9.6 whatever grams of sugar on average. How often did we see something like that or even worse in our simulation? Because if we do see it decently often, that means that maybe it was just due to randomness. But if it's quite unlikely that our model of picking random shelf 2s predicts that, do you see how that would lead us to an alternative idea? Like, all right, maybe there was some nefarious work going on here. They were trying to get the kids to get their sugary cereals and to ask for them. So try that. Think about it. I try to do whatever this thing thinks is wrong with my account. Okay, okay. Mm-hmm. Yes. Let's assume that it's fine. I'll have to fix that later. I'm gonna try to do that simulation. We've got plenty of time. I'm here to help if you have any questions, but it's gonna be very similar to the ones that we've done, especially that midterm scores example. So it's like you're not just making a, what is it? Section 3. You're not making a random section 3, you're making a random shelf 2. It's pretty much the same. I don't remember. I'm not going to look ahead and see, but let's see if that p-value is really, really small or decently large. Was it likely to be predicted? That's my timer. Did we do it? Did anybody get a p-value they're willing to share? Was it small? Was it large? Or did we get stuck? Well, do shout out if you're having any questions, because I can't tell if it's just like super easy or you're not getting it at all. So I cannot predict, but I want to try it. I want to do it with you. So yeah, let's try to do that idea, right? So okay, if under the assumption that this was all just due to randomness, shelf 2's high average sugar content, that means if I were to make another random shelf 2, then I should see sometimes a large amount of sugar in it. And the way to make a random shelf 2 is like take everybody on any, because like we're kind of assuming that the shelf didn't matter. Go and take a sample of the cereal data set. Go and sample exactly as many things as were on that shelf. 21, right? Don't clone any cereals. They're all different, right? It's with replacement equals false. I hope you see why. And so here's 21 random cereals. They were on different shelves. It doesn't matter because we're assuming the shelf didn't matter, right? We're assuming that, all right, just they took random 21 cereals from the loading dock and shoved them onto the shelves. So here's my 21 random cereals that we're pretending are on our new simulated shelf 2. Go to the sugars column, right? Get the sugars on that random shelf 2 and get the average. Does that make sense how you'd want to simulate with that kind of process? It's the same amount of cereals, get 21 of them from anywhere, because we're assuming they just took random ones to place on that shelf, and get their average sugar content, see how much was in it. It looks like it was decently close to 9 for this one, for this sample, but if you do it again, of course, maybe it'll be a bit smaller. That's the thing. So these are a bunch of average sugar amounts, and these are simulated shelf 2s. Let's simulate 10,000 shelf 2s. That's our magic number, right? That's what the book likes to use. That's what we've been using. So let's make a function, right? Let's call it give me one simulated average value. Oops. And as the body of that function, I just kind of want to give back, return that idea, right? There's my average values. And then I want to simulate 10,000 averages. So it's always going to be like this. Similar idea, I can copy and paste 10,000 simulations, but I'll call them simulated averages this time. Simulated averages, one simulated average. That should do it, I think. And 10,000 times, if I do that, it takes a while to take samples, and so that's why it's still running. But eventually, here's 10,000 simulated shelf 2s and their average sugar contents. Does that make sense how you do that? Questions about that? Because then you hit it with a histogram, you see a p-value, it all works out. So let's call this column averages, give it simulated averages. So there's just a table with one column with all the things that I've simulated. Give me a histogram with column 0, and we can do 20 bins again, as we like to do. And the average sugar amounts on these simulated shelves, how does it compare to the 9.61 that was in real life? Where's 9.61? It's over here. Potentially we've gotten a shelf randomly with that much sugar, but it's very, very unlikely to see that. Super duper unlikely in our simulation. Even 10,000 times. How often did this happen? How often in our simulated averages, how often did we see a value that was equal to this weird number that was very large, or even worse, right? Even more extreme, bigger than. So we can do that, play that kind of game. We can np.counting on 0. How many trues did we get? 6 of them out of 10,000. Len simulated averages, right? That is what? 0.06%. So significantly less than 1% of the time did this happen by chance. It's not that it's impossible. It's always possible, but the question is, how likely is it? This is ridiculously unlikely that we were in one of these universes, right? 6 out of 10,000 chance. Does that make sense? So that means we should reject our null hypothesis. It was very, very likely that the average sugar was not due to just randomness. They probably were trying to make shelf too super sugary. Yeah. And so that's our conclusion. That's what we take away. And that's how we do that kind of simulation and test. Yeah. Are there any questions about how those ideas turned into code? Can you see it? Going from this to the function, to the p-value, all those fun things. Because that's data science. It's fun, right? I hope it's fun to you. That's us asking questions and getting a legitimate answer to those questions. How likely was this to take place? And so without a doubt, we can know, like, okay, was this probable? What does that mean for us? How much are we willing to accept? What's significant for us? This is pretty darn significant, no matter how you swing it. So that's pretty cool. All right. And that leads us to the end, finally, of chapter 11. We know how to test hypotheses in a bunch of different ways. You got your sample proportions. You've got your pick random shelves. Just like take from the original full population, assuming that the shelf didn't matter, assuming that the section didn't matter, assuming that the fish diet, amount of fish in your diet didn't matter. All those things. Yeah. So yeah, with that, I want to release. It's time now. This chapter was needed to complete homework 6 and lab 6. So let's get some due dates for those. And that's all that I have. But you please ask me questions if you have any. But let's take a look at our schedule. Homework 6 and lab 6. So let's see. We are where? We're 316. Let's do, I like to do Wednesdays and Fridays, right? So let's do homework 6 due on the 25th, and then lab 6 due on the 27th. All right? So that's when I'll do those. Let's homework 6 first, then lab 6. Remember that they're already out. They just need due dates. We're going to do 25th for homework 6 and 27th for lab 6. 25th. And then 27th. And that should do it. And I think that's all that I wanted to talk about. Any last questions about chapter 11? Hopefully you've read it by now. It's a good one. It's very powerful, the stuff that we just learned. But there's more where that came from. We'll get into the next one next time. And I think that's all that I officially wanted to say and have recorded. So let me stop that.